My name is Nick Delurgio. Hope everyone is having a good start to the quarter. I'm going to give my first presentation on the research I'm doing in my 290s, which is on dynamics, control, and reduced order modeling for distributed space systems in eccentric orbits. So the motivation for this project comes from earlier this year when Shane published a paper which enabled rapid mission design for the SwarmX mission. Through the use of reduced order modeling techniques, Shane was able to achieve simplicity and efficiency in prototyping the relative orbit design for SwarmX, allowing him to rapidly iterate through different swarm configurations, swarm control windows, yada, yada. And it really helped with the design process for SwarmX. So the natural next step off of this work is to expand it to handle orbits of arbitrary eccentricity, because what the original paper assumes is that you are in a circular orbit. So the objectives for this project are to introduce relative orbit elements and the corresponding state transition matrices that are appropriate for eccentric orbits, and then move on to developing strategies for swarm configuration maintenance, particularly in eccentric orbits, and as well as creating reduced order modeling tools in order to simplify the mission design process as much as you can, while not being bounded to a circular orbit, also considering the eccentric orbit case. The limitations of this work is that I rely heavily on the use of linear relative motion models in order to reduce the order of the model, which requires small interspacecraft separation. So that's one limitation. And so far, I'm only considering J2 perturbations in this analysis. That could potentially be expanded to include additional perturbations in the future, but for now, just J2.
Yeah, careful about saying more interspacecraft separation. We have seen in class that that's not the case for what we have seen the beds.
Yeah. But particularly with the linear state transition matrices for, we'll talk about it, but yeah. There are some niches there. Yeah, so on the agenda, so it's a pretty broad set of topics today. I'm going to start off with a review of the literature on linear models for spacecraft relative motion. Then we're going to move on to where my contributions start, which is on the introduction of some new relative orbital element sets that are have some nice properties in eccentric orbits. Then we're going to start discussing J2 perturbations in eccentric orbits and some formation design strategies that go along with those perturbations. Then we'll move on to swarm maintenance control schemes. And then at the very end, we'll finally touch on where this project started, which was reduced order modeling. And I have a short scenario set up to show the power of the model. So yeah, we'll get started on linear models of relative motion. I'll keep this part as brief as possible, but to start, in the 1960s, the Hill-Clawhessy-Wiltshire model was introduced to enable rendezvous proximity operations and docking missions, particularly for circular orbits, making that assumption. For completeness, I put the model here, but we are not using it in this project. And the main takeaway of this model is that the integration constants introduce important characteristics on the geometry of a deputy with respect to achieve spacecraft in the RTN coordinate frame. So I put that definition here where the integration constants define a semi-major axis of an ellipse in the RT frame, as well as a semi-minor axis and the bias, the linear transformation away from the center of the chief, all defined by integration constants here. Same with the RN plane. The same applies where these integration constants have really interesting geometric properties. It only accounted for circular orbits. So a natural expansion on this was introduced by the Yamanaka-Ankerson model, which was developed in the early 2000s. And the advantage of this model is that it can handle orbits of arbitrary eccentricity. So it's a new model here, which I put as well, with a new set of integration constants. And one of the differences between the CW equations and the Yamanaka-Ankerson equations is that CW equations rely on time, and the Yamanaka-Ankerson model is a function of true anomaly instead. It's directly on location in orbit rather than parameterized by time. So that's one interesting property. A limitation of this model is that it relies on true anomaly, which is not well defined in circular orbits at E equals 0. So it would not work extremely well in that case. But I mean, it was built specifically for eccentric orbits, so that's all right. Once again, there is a geometric interpretation of the Yamanaka-Erickson integration constants, and we'll discuss this much more in detail in a second. But it's not showing up here for some reason. But rho is equal to 1 plus e times the cosine of true anomaly, which means that you can see that in the semi-major axis here of the RT ellipse, this changes as a function of your location in the orbit, which means this is not actually the geometry that a deputy would follow with respect to the chief. And we'll discuss that in much more detail in a few slides. So that is the caveat here. So one of the contributions that
Go back one slide.
Yes.
The fact that it's in raw, it's embedded the anomaly, which is the second frequency.
Yeah.
So it's a bit deceptive.
Yeah, exactly. So
it doesn't show the second.
Yeah, it only shows the first frequency if you fix rho at a certain point in time. But in reality, as you move around the orbit, it expands and contracts, and it generates some pretty interesting shapes. Fixing rho is actually a very useful strategy that we can use for mission design, and we'll talk about that in later slides. So one of SLAB's contributions to the state of the art is removing the singularity of the Yamanaka-Erickson model at eccentricity equals 0 in a circular orbit. And this has been done by two people in the lab, Tommaso Hufanti and Matthew Willis. And they had very similar strategies resulting in similar models, which are borderline equivalent, but have some slight differences. But in my work, I'm working with the model that Tommaso introduced. So that's the one I'm going to discuss here. So the trick that you can do is you can perform a rotation of the Yamanaka-Erickson model by this rotation matrix right here, which allows you to transform the reliance on true anomaly into a reliance on the true argument of latitude instead, which is defined well in a circular orbit. So by performing that simple transformation, we can arrive at a new linear model where rho has a different definition in terms of the relative or the absolute eccentricity vector and true argument of latitude. And this will work in both circular orbits and eccentric orbits. So this is the linear model relative motion that I am going to use in my work. All right, so we're going to move on to relative orbital elements now. So ROEs are a function of the chief and deputy orbital elements. You can define these ROEs in pretty much any way you want, however is convenient for your work. But there are some ROEs that happen to share a first order equivalence with the integration constants of known analytical solutions. And what that means is that you can essentially, under the closeness of spacecraft assumption, you can substitute their ROEs in place of the integration constants, and then just use a linear model that way, which is an interesting property. And this has been done by several people. Professor D'Amico introduced a set of ROEs that share a first order equivalence with the CW integration constants. Joshua Sullivan in his thesis introduced a change of variables from this set of ROEs into what he denoted eccentric ROEs, EROEs, which share a first order equivalence with the Yamanaka-Erickson integration constants. So those are two options. I'm not going to use either of these, though. This is just for literature review. And this is the point where we start transitioning from what's in literature to what my contributions are. So I'm going to introduce two new sets of relative orbital elements here. A singular set and a quasi-non-singular set. So a few properties. The quasi-non-singular set is a function of a quasi-non-singular set of absolute orbital elements, which uses the eccentricity vector and mean argument of latitude. So U is mean argument of latitude, then you have EX and EY in different parts of this model, while the singular set just uses the classical set that we're all familiar with argument of perigee. Eta here is just 1 minus E squared, square root of that. And these two sets both share one thing in common, and that's they're first order equivalents with the integration constants used in the model that Tommaso developed. So that immediately means that they have geometric meaning under the closeness separation. And a few properties, despite Tommaso's model working in a circular orbit where E equals 0, the singular set is not defined, not uniquely defined once the eccentricity gets small. The quasi-non-singular one is. It is a little bit more complicated. We'll talk about the advantages and disadvantages of each of these in a little bit. But one advantage, quasi-non-singular, is it's universally applicable as long as your eccentricity is less than 1. And another interesting property of both of these is that you can see that the mean anomaly or mean argument of latitude appears in 3 of the variables rather than just your relative longitude. So in a circular orbit, you would see that it only appears in 1 term, but in the central case for these ROEs, it appears in 3. And that's consistent with what's been seen in Matthew Willis's work, Joshua Sullivan's work, and Tommaso Hufanti's work, is that these 3 integration constants are time-dependent integrals. And under Keplerian motion, if you have a difference in semi-major axis, all 3 of them will drift, which is just the nature of an eccentric orbit, and it leads to some interesting properties. So these are the 2 that we'll be working with in this presentation. This is not super important, but just to demonstrate, if you know your chief orbital elements, both ROEs are affine combinations of deputy orbital elements, which is just a way to show that it's easy to translate in between ROEs and deputy orbital elements or vice versa. It's easy to recover one from the other. Not a problem. All right, let's talk about geometry. So our favorite term, rho, is appearing once again. So if you fix rho, you can get nice ellipses like this, but in reality, as the spacecraft goes through an entire orbit and true anomaly changes, the properties of this ellipse expand and contract. And that means that it does not actually follow an elliptical motion. I put the definition the correspondence in between the relative orbital elements and the RTN position as well, just here for completeness. And if you were to generate a few examples, I just generated a few examples to show you what this motion actually looks like in a few cases for eccentric orbits. For example, you could have something that looks like an ellipse in an RT trajectory, but has a huge bias towards one side. The RN trajectory, clearly not an ellipse. The bias could be other way. You could even have a downward shift. This really ends up depending on your argument of perigee location is what that ultimately comes down to. RN trajectory can have some deformed shape. So it's a little hard to work with. Matthew Willis and his thesis put together a nice plot of these to show how increasing eccentricity increases how the ellipse deforms over the course of an orbit, and the direction in which that deformation happens as a function of 2 integration constants, which is approximately equivalent to just the direction the argument of perigee is oriented. So you can see that does not happen at E equals 0. It's the same every time, but there's clearly a deformation in eccentric orbits. It is useful for the purposes of mission design to once in a while just fix rho so that you get a geometry that's more easy to understand. So the minimum and maximum values of rho are 1 minus E and 1 plus E, which is easy to see just from apogee and perigee. And this has several applications. As Tommaso showed in his thesis, what you can do in order to get the minimum RN plane separation over the course of an entire orbit is set rho to its maximum value, which yields minimum separation. I put it in 2 forms here. So the RN separation is this linear function right here. And if you take the singular value, the minimum singular value of this matrix, you get the minimum separation. So by increasing rho here, you can quickly see that that's just going to reduce the singular values of that matrix, reduce the minimum separation to its smallest value. And that can also be put in analytical form right here as well. All right, we're going to move on to discussing J2 perturbations now. On these new sets of ROEs. So to give an example of a nonlinear, okay, so first of all, I'm only going to be considering secular J2 perturbations because the periodic effects in relative motion, for the most part, will cancel out. So this is the definition of the secular J2 perturbations on absolute orbital elements applied to both the chief and the deputy, right here, where you have some coefficient as defined here. And if you just take the time derivative of this and then substitute in these values, you can arrive at something like this, which is just a nonlinear, which is a nonlinear dynamics of, in this case, the singular ROE set. And you can do something similar for the quasi-non-singular one as well. I did not show that here. We would like a linear version for the purposes of mission design and reduced order modeling. So when you perform this linearization, you will find that in an eccentric orbit, that linearization, if you put into a form x dot equals ax, it yields a time variant system, unlike in a circular orbit where it is a time invariant system when you apply it to this set of ROEs. So the trick that we do here is to take a different set of relative orbital elements from literature. So I took a matrix straight from literature that was derived from a time invariant set of ROEs. And because of that, you can do this trick where you take my set of ROEs, transform it into the time invariant set, essentially propagate it, and then convert back into the ROE set that I'm using. And so I took this straight from literature, and then I found the rotation, the coordinate transformation to go in between sets of ROEs, and ultimately arrived at a state transition matrix for my two ROE sets. And this is valid for both because they share a first order equivalence. So there's a bunch of substitutions here, and we're gonna now talk about how these, what this state transition matrix.
This is the point of the fifth slide. When you map the relative position of relative velocity, you make an assumption of small separation.
Yes.
But when you propagate the ROEs in a linear model, you only neglect the one of the effects in some orbital difference.
Right, right.
Because it's an important map. So these mathematics is valid for much larger separation in general. Actually, for Keplernian motion is all the only second order effects are in the different semi-difference.
Yeah.
Here we were coupling. So that's what I meant, that it's not in small interface of separation across the board.
Okay, yeah.
Not for propagation, but for mapping to the position of the
Right, yeah. So for ROE propagation, this is valid for pretty large separations, but not necessarily the mapping from ROEs into the RTN frame. Yeah, okay, that's important to note here. Let's study these dynamics a little bit. First of all, let's look at relative longitude, which is this line right here. None of these coefficients include time in them, so don't worry. I'm excluding them so you can clearly see what's going on. In this linear model, that's just going to either increase or decrease linearly with time, pretty straightforward. Delta IY, the difference between ascending nodes, essentially, is also linear, where it's multiplied by time, so time derivative, that's quite obvious. And you can see that in this graph right here, where your delta IX is fixed. It does not move under J2, but this will drift either upwards or downwards depending on your ROE choice and the properties of your orbit. Relative eccentricity is quite interesting. So first of all, you have some trig terms in here. So this causes a rotation, like a periodic effect over long periods of time, a slowly drifting rotation, which is this component right here of the time derivative of your relative eccentricity vector. You can just see that in these trig terms, multiplied by the rate of change of the Chief's argument of perigee. But then what's interesting in eccentric orbits, and this is not true for circular orbits, is that these coefficients, the amplitudes of these trig functions also increase with time. There's a secular effect going on here, which does not happen in circular orbits. So not only do you have this rotation, but you also have this secular effect that's causing the magnitude of your relative eccentricity vector to grow as well. So if you simulate this, for example, you'll see that this causes over long periods of time, this was propagated for 200 days or something for an arbitrary set of ROEs, you're going to get a spiraling effect. And over time, that means that the spacecraft, even if you have zero difference in semi-major axis, they will get farther apart, which is a little bit inconvenient. So that's an interesting result that you can clearly see from this choice of ROEs and through the state transition matrix. I think it's worth touching on the accuracy of the quasi-non-singular ROE and the singular ROE. So on the right-hand side, we have a graph of the nonlinear secular J2 effects on the quasi-non-singular ROEs. So that's the blue line. And then you have the linear version, which is just taken by using the state transition matrix. So nonlinear versus linear. So for a moderate separation, we're looking at around 20 kilometers on a pretty large orbit, semi-major axis, 22,000 kilometers with an eccentricity of 0.7. So it's relatively large. You can see that it matches up pretty well. This is propagated for 2,000 days even. So those two effects hold up for long periods of times. Note that this nonlinear one is only including secular J2 effects. So if you were to include other perturbations, those will not be the same. But this is just to demonstrate the equivalency is quite good under a moderately small separation. If we increase that though to this is around 200 kilometers of separation now is what we're looking at. It's not too good. That linearization does not hold up very well here anymore. So I should note these y-axes are in kilometers. So we're, this quasi non-singular set is not mapped very well to the linear set under this larger separation. And that's kind of expected. We wouldn't really expect it to be great under that sort of separation.
So that you have compared with the previous testing. And okay. So you have increased mainly the relative eccentricity vector.
That is correct. Yeah. The other ones, there's a coupling between all of these, so they stand. But yeah, like those two stay in the same order of magnitude. But it's really increasing the eccentricity will cause this to become less accurate. Yeah, if you were to scale it up to land, it would probably hold up a little bit better.
Because you're moving the relative perigee around.
Yeah.
So they're all like pretty far apart.
Well,
or the eccentricity, depending on what they do.
Yeah, I'm moving the relative eccentricity part, which means that it's just really just.
It means there, but difference either like argument of perigee or fixed or
exactly the argument of perigee.
Yeah, you're saying
the argument of perigee is going to rotate at different rates each of them, and that causes the linearization not to hold up too well. So you have to be a little bit careful, certainly, by increasing that. But what's quite surprising actually is that the singular ROE set, even at the exact same set of ROEs, holds up significantly better. Yeah, exactly. Which was almost expected. So exact same set of ROEs as the last one, except this new set, the singular ROE, is actually a quite good model at this larger separation. And this is a general trend that you can see if you test different cases as well. I've found that this is in general the case. And so that gives you even if your temptation is to use the quasi non-singular set for everything because it works for all the cases. The singular set's actually has a better linear approximation, which is something to account for when you're choosing your choices of ROE for emission. Yeah,
this is just for the structure of the STM because what it was saying so essentially because certain rows become important so that they do not. So
yeah, exactly. Yeah, it gets revealed by the structure.
All the other differences are added.
Yeah. So we have a growth of relative eccentricity magnitude and a rotational effect on eccentricity of magnitude for J2. So this promotes the question, how do we design control windows for missions? This is where we start getting into formation design a little bit. So in a circular orbit, what you would do, since you don't have this growth of the relative eccentricity, is you would just bound the phase in between a minimum and a maximum value, bound the delta IY in between a minimum and a maximum value, and then those would be your control windows. And the goal of doing that is to prevent a 90-degree angle from ever forming in between the delta E and the delta I vectors. And as long as that's the case, you ensure a minimum RN plane separation and passive safety for your mission. Since we have since we have a secular effect as well, it makes sense to just introduce a new constraint on your control windows, a minimum and maximum value on your relative eccentricity magnitude. So typically how I could envision this working is you would start, you'd start from some point in here, just following my cursor. You could see it maybe grow over here. Once it hits the Emax, you would do a control maneuver, bring you back to this point. Maybe at the next point, it follows a much more lax trajectory this way, hits the phase bound, comes back here, and then, repeats. And that's not going to be the same every time because your argument of perigee of the chief is rotating. So the amount of growth you get and the relative eccentricity is not always going to be the same depending on the time. So it could really kind of follow any trajectory in here. It will always increase though. Or it could go the other way. You could start from here and go this way if your eccentricity vector is rotating the other direction. So it's just a small expansion upon already known concepts for circular orbits. This secular growth in the relative eccentricity magnitude is sometimes a problem. So it turns out, if you inspect the state transition matrix, that there are conditions under which the growth of the relative eccentricity vector is 0. It will not grow and it'll just stay fixed and it will follow a trajectory like this in an eccentric orbit in perpetuity. So that's a useful property to have. It simplifies the mission design significantly when you can just have something like this. And there's two conditions here. One is put in terms of ROEs and one is even simpler, put in terms of orbit element differences. And if this condition holds, delta E will stay at the same magnitude in that configuration. So that's a useful effect to have.
We have side effects.
Yeah, sure. There are side effects because if you in an eccentric orbit, if we go to the state transition matrix, even the inclination is the delta IY is also affected by these two values, delta EX and delta EY. So no matter what, it's going to drift. There's not really a way to prevent that from happening. But yeah. So it does give you a real reason to introduce, like typically in a circular orbit, you would just set delta IX to be equal to 0 to remove J2 effects. But you can actually simplify the dynamics in J2 in eccentric orbits considerably by enforcing this condition on your swarm design. So it gives you a real quantitative reason in order to actually introduce an inclination difference and offset some of the effects of J2, which is kind of interesting. There's a different condition for fixed delta IY formations, and you can hold that variable constant in your state transition matrix by enforcing this constraint on your formation as well. You cannot do both at the same time. So you're going to have to bite it somewhere is kind of this moral of that story. But there are some tricks you can do in your formation in order to make this a little bit easier to work with. One thing that's worth noting is that if you enforce this constraint on your formation, a lot of the more challenging reduced order modeling problems in eccentric orbits reduce to extremely simple reduced order modeling problems, very similar to what Shane introduced in his work. So that's another reason to do it. All right, so we're going to go on to a discussion of control specifically applied to swarm maintenance. And I'll talk about why I'm putting that, it's not generalized, it's specifically applied to swarm maintenance in a second. So first of all, we need to get a control input matrix for these new ROE sets, and you can do it by taking, to use the chain rule and computing this. So what this gamma matrix does is if you apply a delta V in the RTN frame to your deputy spacecraft, it'll then introduce a change in relative orbital elements known as a pseudostate through this matrix, essentially. So you can apply this rule, and I did it for the singular set. I haven't done it for the quasi-non-singular set yet because that derivation involves a more complicated set of ROEs, and it's a little bit harder to manage. So that's a work in progress. But for the singular set, you will arrive at this. And it's a singular set, so we expect it to break it equals 0. So we can check, and there's the E in the denominator right there. So that'll blow that up. If I were to do the same derivation for the quasi-non-singular set, it would look very similar, but would not have this issue right here. There's an advantage of this set of ROEs in that the in-plane and out-of-plane control is decoupled. So you can handle the out-of-plane motion and the in-plane motion using separate control strategies, which is useful. And if you're familiar with Michel Chernik's work, you would actually notice that this control input matrix shares a lot of similarities with previously derived ones as well. There's some useful similarities here. Delta V lower bound. So this is where I kind of started trying to work on some optimal control things. And if you take this control input matrix here and you try and do an in-plane delta V lower bound using only tangential maneuvers, you can arrive at delta V lower bound, which is very, very, very similar to what's been done in the literature previously, where you can arrive at something like this. And there's one that's very useful for circular orbits that's used in order to size maneuvers just based on your desired maneuver scope. But this is similar to what Michel derived for eccentric orbits as well, just with a few etas sitting around in different places. That's the only real difference. The problem in eccentric orbits, though, is that this delta V lower bound is almost never reachable. In the circular case, it typically is reachable, and that enabled Shane in his reduced order model to use that equation in order to size maneuvers and do quick, if you have this set of delta change in relative orbital elements, you could quickly get a maneuver from that. But I would not say it's sufficient just to plug this into a reduced order model and expect it to output the true delta V. For example, like if you were to do a change in relative eccentricity, you can almost never fire in the optimal direction here. Like that's just, you have to align your maneuver with the desired phase of that change. And that's pretty much never going to be at this exact value, depending on what your maneuver is. So that poses the first challenge here. What I've done in order to simplify the problem for the purposes of swarm maintenance is split it into 3 subproblems, because as you're performing swarm maintenance, what you do is once your relative longitude bound gets exceeded, you perform a relative longitude reconfiguration where everything else is fixed. And then same for relative eccentricity and same for relative inclination. You can split those maneuvers into 3 parts, and those smaller control problems are a little bit easier to solve rather than the broad control problem in eccentric orbits. So this first one is a pretty straightforward one that everyone is probably somewhat intuitive, where, in order to do this reconfiguration, you have to do a change in your semi-major axis, let the relative longitude drift, and then eventually, once you get to your desired longitude, you just fire again, restore semi-major axis equivalence. In order for it to be optimal, you have to fire at perigee because it's in an eccentric orbit. So that constrains what delta M can be to be an integer multiple of 2 pi. And as long as you follow that constraint, you're going to be optimal and you can do your reconfigurations. That one's pretty straightforward. This one is less straightforward. So in order to perform a relative eccentricity reconfiguration, the first assumption I'm going to make is that we're only going to use tangential maneuvers to perform this in order to do this realignment. And something that Michel showed in her work is that that is marginally suboptimal. You're going to get a slightly higher delta V by doing that. It is very, very small. Yeah. So for the purposes of this work, I think it's perfectly acceptable to size maneuvers off of just using tangential maneuvers for relative eccentricity. So in order to compute the location at which you fire these maneuvers, you need to align your maneuvers in a way where when you perform that tangential maneuver, it fires in the direction of your desired pseudostate phase. So this right here, you're going to have a specific phase direction. And then using the bisection algorithm, you can quickly compute where that true anomaly exists in order to get that maneuver in the direction that you want. There is an analytical solution that also exists. It's very long and complicated, and I have not derived it for my set of ROEs yet. But when you actually implement it on flight software, you want to use the analytical solution. Don't want to put on a slide though, so I'll stick with bisection for the time being. When you do the bisection algorithm, you're going to find that there's 2 valid solutions for this per orbit, and then you can just increment that by 2 pi depending on your control duration to get all the possible maneuver locations where you can perform that maneuver. And since you're aligned with the pseudostate phase, if you reach a specific change in delta EX, you will, by definition, also reach that same change in delta EY. So that reduces the number of maneuvers you need to perform from 4 to 3. So then what you can do is you can iterate over all the possible values of true anomaly in order to find the minimum of all the different ones, and you can arrive at your minimum solution. No guarantees on optimality with that configuration, but you will find the minimum set in order to you'll find the minimum set in order, or the minimum true anomaly locations in order to get that maneuver completed. And since this is just for delta E reconfigurations, your change in semi-major axis and your change in relative longitude will be 0 here. But in general, you could actually set those to small values as well and also achieve that change. For example, let's set a desired pseudostate, and let's set a desired sheaf orbital elements. From running the bisection algorithm, you'll arrive at 2 true anomaly locations, which are the first 2, and then I just added it with third for this example. So the first 3 possible times at which you could fire. From those true anomaly locations and where you're starting in your orbit, you can arrive at 3 possible times. And then you can just solve that linear system in order to figure out what the 3 tangential maneuvers are. So in this case, you would arrive at these 3 right here. And since they're tangential maneuvers, you just take the L1 norm of this vector, and then you arrive at your total delta V. And that's kind of what you need to do in order to size these maneuvers in eccentric orbits, rather than having a nice closed form solution that's always single equation that's always guaranteed to be accurate. So that's what we look at there. Quickly, we'll go over relative inclination maneuvers. So it's a single maneuver since it's out of plane, and you can determine the maneuver location just by, once again, just taking the arctan of the pseudostate, and that's actually equivalent to true argument of latitude here. You can see that the maximum effect of this is going to be at apogee, but typically you actually need to fire in a different direction in order to complete that maneuver. In order to complete that maneuver and get to the desired pseudostate, so that's not reachable either. There's a common case where delta IX is equal to 0. And if you plug that into this equation right here, you're going to arrive at this sizing equation where your maneuver magnitude, which is just the out of plane delta V, corresponds to this change in delta IY. And you can see that you can minimize that delta V by getting this expression to be 1 minus E, which would happen at minus 270 degrees. So potentially, if you're planning on doing a lot of out-of-plane maneuvers, you might want to design your chief orbit around that in order to reduce the cost of your mission. All right. We're finally at the promised land, reduced order modeling. So the way I view the reduced order modeling problem for mission design is in 2 components. So there's a swarm maintenance part of the reduced order model, where your inputs are your chief orbital elements, your deputy ROEs, your control window sizes, and the configuration time duration, how long you want to hold those control windows for. You run it through a reduced order model, and you arrive at the following outputs. First of all, you're going to get the minimum RM plane separation over the entire control window, the maneuver times when you're going to execute maneuvers in order to keep yourself within that control window, maneuver locations, so where you actually fire those maneuvers in the orbit in order to ensure that you stay in the control windows, which is different from maneuver times, and then maneuver magnitude, maneuver delta V. There's another part of this, which is specifically in swarm reconfiguration. So the goal of this would be to say, all right, we have an initial set of ROEs, and we want to get to a final set for some arbitrary configuration, whatever it is. Run it through a reduced order model in order to get to the maneuver locations, maneuver delta V, and the amount of time it takes in order to complete that maneuver. I view those as two separate reduced order modeling problems. This first one, I'm pretty much got complete. This second one is not yet finished, so I'm not going to be discussing it in this next section. And the reason it's not finished is because of the problem I've talked about with delta V lower bound not being reachable. That makes actually computing for an arbitrary pseudostate significantly more challenging in terms of reduced order modeling. And Michelle solved that problem for a different set of ROEs and has a nice algorithm that's pretty efficient in order to essentially do this. And it would take a significant amount of work that I'm working on right now in order to go through that full reachable set theory analysis in order to finally arrive at that closed form algorithm that I can guarantee is correct for these new sets of ROEs. So that's where the work is happening right now. Minimum separation. So recall the controls. So since we can, the goal is to find over this entire control window where the minimum separation is. And this is actually pretty much identical to what Shane did in circular orbits, because you know that these 2 points here cannot be the minimum separation because there's just a lower magnitude relative eccentricity vector below it. So what you do is you just check these 4 points here, run through all the combinations of those, and compute the minimum separation of that set. And then you also have to check in order to make sure that within that set, a 90-degree angle cannot form. And you can just check the dot products of these two. And if the one's minus and one's plus for two sets, then you know that, okay, somewhere inside that control window, there's a zero separation, which would make that control window a poor design choice. And you can just run it through this very quick algorithm right here, check those 4 sets and get the minimum separation from that. Quite similar to circular orbits. And because we have this useful eccentric control window concept where it's very in parallel with what was done in circular orbits, it's almost as simple here, which is quite convenient. This one's less convenient. So in circular orbits, you can compute the maneuver times and the maneuver frequency easily because the dynamics are time invariant. You can arrive and say, all right, these maneuvers are going to be performed at this rate over it, and then you can arrive at some closed formed expressions in order to be like, this is how many maneuvers are going to be performed over this time duration. Since we have time variant dynamics in eccentric orbits, I would say that's an invalid assumption to make. And you need to account for the change in dynamics. So what this algorithm does is it computes, what it'll do is it will generate a list of maneuvers over a certain time duration efficiently. So what you do first is you compute the time until each of the control window bounds is exceeded. And most of these are easy to compute. This one right here, so the phase bound on relative eccentricity, I've been computing that via bisection so far because I have not found an analytical expression for it so far because the magnitude's growing while it's rotating. It's not as simple as just saying, oh, it's rotating at the rate of the Chief's argument of perigee. That's not true in eccentric orbits. So I've been using bisection for that. If I can find an analytical solution that will make this part even faster, but right now, since you're using bisection, you're running in log n time. But then you compute those 4 maneuvers. So the time till the next maneuver is just going to be the minimum of that set. And then essentially what the rest of this does is just you propagate until that time, reset the orbit elements to what it would be after you perform that swarm maintenance reconfiguration and change your ROEs. And then just recursively do that over and over until you generate the times and maneuver magnitudes over an entire time duration. So where this achieves efficiency for a reduced order model, it does not achieve the same level of simplicity as we had in circular orbits. And I'm going to keep working on ways to make this simpler, but due to the time variant dynamics, it may not be possible to simplify it much beyond this for the purposes of reduced order modeling. It's just a more complicated problem because you have time variant dynamics. Here's a scenario. So inputs are the chief OEs, the deputy ROEs, the control windows, and the time duration. So I set up these chief OEs here. You have a semi-major axis of 10,000 kilometers with an eccentricity of 0.3, some angles. And then you have the initial deputy ROEs where you're starting from, defined here. And we're going to see how we're going to generate the list of maneuvers we need to perform over a 90-day duration, maintaining the following control windows, which I've described here by this graph. So this is the delta E control window, and this is the delta I control window I've set up. Immediately you can see that the minimum separation here is going to be between these two, and it's slightly greater than 90 degrees. So we're going to get a small minimum separation in this example, but it's not going to be quite zero. And yeah, so then the outputs of this are going to be the minimum separation and then the maneuver times, locations, and magnitudes. All right, and then you just run it through the reduced order model and you end up with the following results. Minimum separation, 192 meters, which is small as expected, because we had a very close to a conjunction just for demonstration between those two vectors. And then you run this and you're going to get 7 maneuvers over the 90-day time window in this case. So it'll spit out the maneuver type, the time at which that maneuver needs to be performed approximately. I'm not taking into account, all right, we need to perform maneuver 1, 2, and 3 in order to do a delta E reconfiguration, for example. That's the reduced order model approximation, which is good, which is pretty good as long as your orbit period is small compared to the time in between maneuvers. And then you would arrive at maneuver locations, which I neglected. So for example, relative longitude, you know, that has to fire at 0 and 2 pi to be optimal. Delta IY, you actually have to compute that. This phase maneuver is for the delta E, and I just put the first two, and you're going to actually need to append that with a third one at the end, but that's just plus 2 pi of one of these. And those would be different each time. And then you'll also arrive at maneuver magnitude from what I described and how you separate the control problems into 3 different types of maneuvers. You can just get a maneuver magnitude here, and that'll run super fast, much faster than nonlinear simulation. And you can use that for one of the 2 aspects of the reduced order model, which we're trying to get to, which is the swarm maintenance portion. Like I said, still working on doing arbitrary reconfigurations in between one and the other, but this works pretty well for swarm maintenance scenario. All right, yeah, that's about all I have. So it's future work. I'm planning to expand the state transition matrix to include additional perturbations. And this is not a very hard problem to do because some great state transition matrix have been generated for Professor D'Amico's ROE set. So I can just perform a coordinate transformation on that and get it into my set of ROEs that I'm working with. In order to essentially solve the second part of this reduced order model, I kind of need to go through the reachable set theory analysis and generate, you know, a nice closed form algorithm to compute maneuver magnitudes for arbitrary reconfigurations. I don't think we'll arrive at a simple expression like we have for circular orbits, but as long as we can get something that's algorithmic and pretty fast to run, that'll be good for reduced order modeling purposes. And then I want to validate the current reduced order modeling tools I have as well, which has not been done. And that's going to come through some of my work in 279D, where I can take some of the nonlinear tools I'm developing, validate that the reduced order model actually lines up with what you see in the nonlinear simulation. And we'll be good to go. Yeah, that's all I have. Thanks for listening. I'm happy to take some questions.